Thank you. Thanks, Amber, for the introduction. And I'll also reiterate, thank you, Daniel, for being our researcher spotlight today. We're really happy that you could join us. So essentially, I'm going to set the stage for Daniel, and I'm going to talk about cloud workflow optimization. And I want to do this I won't take too long because I want Daniel to have adequate time, and then for us to have a discussion if there are questions afterwards. So, but let's start with sort of a problem statement. So that's represented by this frowny faced cloud here, and a lot of you may have experienced this, that if you're trying to push through non-optimized analysis, it can really negatively impact your research goals. And what do I mean by that? Well, you could see increased costs from inefficient computation, for example. Egress, you could see egress charges, which are additional charges when you try to move data from one cloud provider to another, which you want to avoid. Or maybe you're not using cloud storage appropriately. You can also have slow time to your results and have missed deadlines. So these are all things we want to avoid. But the good news is that Biodata Catalyst can help you optimize your workflows in a variety of ways. And this will allow you to become a better steward of your cloud credits. So these could be the pilot funds that NHLBI has provided. It could be additional funding from NHLBI. It could be your own funding that you're bringing to the platform and setting up billing groups, for example. So you want to use those funds appropriately, and Biodata Catalyst is here to help you do that. Most importantly, you could become your lab's hero, just like Daniel, and we could highlight you on a community hour session in the future. So what am I talking about? What are the features that I want to highlight? So this is going to be a high-level overview. I'm not going to get too in-depth. There's actually no demo, but I do have screenshots. I want to talk to you about the features that are available on Biodata Catalyst, specifically Biodata Catalyst powered by 7Bridges, that are available to you to optimize your analysis. And I'm going to try to annotate the screen because I'm sorry, guys. And let me switch back there, and I pressed the wrong button. Okay. Does that work? So what am I talking about here? So the features I want to go through are spot instances. Yeah, let me use this instead. Laser pointer. Okay, fantastic. Spot instances. So what are those? These are essentially compute that's on sale for a limited time, and we recommend using those. So BDC allows you to turn those on and use those whenever you feel is necessary. Memoization, and what that is reusing results from intermediate files that you may want to keep temporarily. So if you have a 10-step workflow, it'll allow you to temporarily keep some of the intermediate files, but then have those files expire after a period of either 24 to, I think, 96 hours or something like that. That's in your project settings. And this will allow you to, one, have a task rerun happen faster, but also allow you to save on storage, because those are sort of in a different storage bucket, and those will be removed after a while. Scatter is another feature I want to talk about, and I will mostly be focusing on this scatter technique, which is how you could make your jobs run in parallel and complete faster. And finally, instance metrics. So the metrics are available for every job, and you should look at them. They allow you to monitor CPU, your disk storage, your RAM, so you'll be able to determine, is it just right? Did I choose compute that I'm not even using and I'm paying too much? Or is my machine, or is my analysis getting bogged down because I'm using all the RAM and it's being inefficient? So, well, what if this is kind of too much for you to fast? Well, you can use the public apps gallery, And if someone could put the link in the chat, that would be great, but because it's kind of long. But the great thing about this particular link here is you do not need to log in. So even if you don't have an account, you could sort of browse through the public apps gallery, look up the Bro GATK best practices pipelines, read about them, find GWAS pipelines, etc. And everything in this public apps gallery has been optimized for speed and time. And they're also fully parameterized and easy to run. So I recommend starting there, and then determining, with your pilot test, do you need to further optimize, or do you need to bring your own tool to the platform? You can find the Genesis GWAS pipelines in the Seven Bridges Public Apps Gallery. These were created in a collaboration with the University of Washington Genome Analysis Center. These are sort of highly optimized. They'll work on Google. If your data's on Google, they'll work there. If you're on AWS, they'll work there as well. In fact, there's a guide in our BD Catalyst Git book called Genesis Benchmarking Guide, which talks about how the tools were benchmarked and how they were optimized, and how much they'll actually cost you too, depending on the number of samples, depending on the status of your relationship matrices and some other parameters. So that could dramatically affect the cost as well. But this is already optimized workflow. All right, so when you run a task, you're actually saving, and you have available a wealth of information and a lot of detail. So this is an example of a completed task, and it just so happens to be the Genesis single variant pipeline. Okay, so I see Amber put the slides in the chat, so that's great. There's a lot of links in the chat that are linking to different things. So what else do we see? One, we see the price. So price is a sort of a metric about analysis optimization, right? So because you're essentially renting a compute node for a amount of time that you need. So it's a measure for how optimized you are essentially. We have, and this will actually break it down further. Every task you can see how much was I charged for the compute, how much was I charged for the temporary storage, and what was there any data transfer charge. So this should always be 0. You should go to your project settings and change, or rather create a new project that might be on Google or Amazon or vice versa, depending on if you should never see a data transfer charge, or at least try to minimize those as well. The other thing I want to point out is on every task, you can click on the View Stats and Logs screen, which is a new button here. Or it's not a new button, it's just a button that's available on every task. And what does that look like? It takes you to this view, which is a dynamic view, which will show you a timeline of your analysis. And you'll start to see these stacked up green lines, essentially. The green lines are stacked, meaning that the job is completed, and you want to see as many stacks as possible, and you want to avoid, wherever possible, serial green lines. We're going to get into this in the next few slides, but it's a really important view to help you optimize. You, of course, have your job resources that are available in this view in real time if the task is running, or saved if the task is complete. So you can go back and see, was my task optimized? Could I have done better? Could I have chosen a different compute, or etc. You'll also be able to see the task logs. This is helpful if the task fails and you need to troubleshoot. You'll be able to see the error messages in the View Stats and Logs screen. Okay, so let's talk about, Daniel's going to get into another great example, but we have a fellow from cohort 2, that was the Seven Bridges fellow named Ina at Harvard Medical School, and she actually published a workflow on DocStore called Ancestry Math Workflow. I think it has a better name on DocStore, but it's a workflow that allows you to calculate ancestry-specific allele frequencies in admixed populations. And she was having issues getting it to run performantly, and eventually she was able to exceed the performance from her local cluster, but it took some revision. So you can see this, revision 26. So there's a lot of trial and error that goes on. And one thing she noticed was her local analysis has a tool called VCFR. And if you see, the cost was rather dramatic for such a simple step. She then replaced that with a tool from the public apps gallery, which was pre-optimized or potentially a better fit, and you'll see a dramatic reduction in cost and time as well. So this is using the Nomad. She was processing Nomad here. So it's exact same input files, but dramatically different cost. All right, so scatter is a really important tool to optimize for both cost and time. So what do I mean by that? Well, let's take, for example, a really typical Amazon instance called C4.2x large, and there's like 100 of these. They're just different amounts of CPU and RAM and maybe some GPU and storage. They're optimized for different things. C stands for compute, so they have a higher ratio of compute to RAM. But this is generally a sort of a workhorse thing. But if you're not using the CPUs efficiently, you're not optimizing for cost or time. So your job's going to take longer, but you're also being inefficient as well. So you should turn scattering on to be able to use the one CPU per job. And you could go in and look at your task logs to see, what percentage of all the CPUs was I actually using? Should I use a lower powered machine, or should I just try to use a technique like scattering to use more of the CPUs at any given time? There's a manual on our Git book on Biodata Catalyst called Comprehensive Tips for Reliable and Efficient Analysis Setup, which goes into more detail about this. Once you've optimized a specific pipeline, then you could use batching, which creates analytically identical tasks. So for example, you may want to process each chromosome the same way, but then in each pipeline, you're being really efficient about using the CPUs the correct way. Okay, so how do you turn on scattering? I'm not going to demo it today, but I have a screenshot. So here's, for example, the pipeline, a pipeline at the center of which is using GATK4 haplotype color. That's represented by this circle here. And let's look at what are the inputs. So we have a input cram, which is being changed to a BAM file, and that goes into haplotype color. Then we have, of course, the human genome reference, which is an input to haplotype color. And then we have an array of intervals, which represents different sections of the human genome, which are being added to haplotype color. So what we're going to do is when we double click on this node, we have some tool details on the right, a little window that pops up, and then we could select what input node we want to scatter on. And we just highlight include intervals. So what this is going to do is run haplotype color once for each interval file. And that's how you can easily increase your optimization without ever even changing the command line for GATK4. Now, GATK4, haplotype color may have other ways to parallelize, but this is just a quick and easy way to do it without having to change your command line. Now, every scatter step is usually followed by a gather step. So that's what this third app is, GATK4 merge VCFs. It takes all the individual VCFs and merges them back together. Okay, and so this is how Inat from Fellows Cohort 2 was able to get her app to run performantly in the cloud. And so she made a sort of a utility app that took intervals that she was interested in and broke it up into multiple files. And then the platform saw each of those files, scattered, and ran one job. I think there was 300 or 400 different intervals she was interested in, and it was able to run a lot of it in parallel. That's when you see the vertical stacks. Horizontally, that represents serial analysis, and you can't always avoid it, but you want to try to get as much parallel processing as you can. Okay, so that's it. I want to make sure Daniel has plenty of time. And of course, if there's questions, I can answer questions after Daniel's presentation. But let's talk about next steps. So like Amber said, please make an account on the Biodata Cows ecosystem, which is the homepage. Take a look at our public apps gallery, which the link is in the chat, so you don't even have to log in to see those apps, such as the Genesis GWAS apps. Join Biodata Catalyst powered by 7 Bridges office hours. So these are different than community hours because they're not unscripted. So people show up, different amounts of people show up different times. Currently, they're on Google Meet, but we're going to eventually move that to Zoom. They're held 10 a.m. Eastern Time Tuesdays and 2 p.m. Eastern Time Thursdays. You can just drop in, and if that doesn't work for you, book a consultation time with either RT or myself, and we'll talk about how we can help you stand up your analysis or optimize your analysis. So with that, I am going to hand it over to Daniel, and thank you so much again for being our researcher showcase. Daniel, would you like to control your own slides?
Sure.
Okay. Amber, can you make him a co-host?
Yeah. Let's see. There we go. Should be good to go.
Thank you.
Okay. Okay, so today I'm going to talk a little bit about my project, which is looking at genetic variation on looking at the impact of genetic variation on cardiometabolic traits in ethnically diverse African populations. It's mostly going to be focusing on the technical side, so not really any cool, exciting results, but some important optimization that I've had to do in order to get one of the what is normally seen as a fairly basic program, but can be very computationally intense to run to be able to work on my data set. The data set that I'm working with is from the Transomics for Precision Medicine, or TopMed program. So if you're not aware, I'm working the freeze of the data set is freeze 10, which is quite a large data set of high coverage whole genome sequencing. And in freeze 10, we have up to 180,000 individuals, and we have about 900 million genetic variants, which is just really rather remarkable. Obviously, some of these genetic variants are overlapping and have the same position, but we're getting close to the point of having nearly a third of the human genome covered by variable sites in this data set, which is just remarkable for me to think, because the first data set that I used in graduate school had about 150 people, and that felt like a good size at the time. And now here's one with 180,000, and it's a really remarkable data set to get to work with. And within TopMed, I'm part of the Africa 6K project, which is led by my postdoc mentor, Sarah Tishkoff, here at the University of Pennsylvania, as well as our co-PI, Scott Williams. And so our data set includes up to 6,200 individuals, and it's a rather remarkable data set in order to be able to look at African genetic diversity. And that's because it includes almost 230 different ethnic groups coming from primarily Botswana, Cameroon, Ethiopia, Ghana, Kenya, and Tanzania. So this really does give us a unique opportunity to be able to look at genetic diversity and how that diversity impacts different traits. And so the goals of my project are first going to be to characterize this genetic diversity, and then to run scans of selection so that I can hopefully identify genetic variants that are associated with different biological processes. And then ultimately we'll be integrating this high coverage whole genome sequencing data with high throughput proteomics to be able to identify genetic variants that are also associated with changing protein levels. But today I'm only going to be talking about the first element of my project, and that's being able to look at the genetic diversity in this cohort. And in order to look at the diversity within this cohort, I'm going to use a program called admixture. And I'm going to use admixture to model and approximate the genetic ancestry of the individuals in our data set. And the output of admixture looks something like, or we can visualize the output of admixture so that it looks something like this. If we were to read an admixture plot from this paper from Fan et al. In 2019. Each bar is representing one individual, and the colors are representing different admixture modeled ancestries. And so the quantity of that color for one single bar would represent the proportion of that individual's admixture modeled ancestry that can be assigned to different admixture modeled ancestral populations. And admixture as just an algorithm is a clustering algorithm where we assign a specific number of clusters, or K, so the number of clusters or ancestral populations that admixture will then fit to your data. And when we apply this algorithm to a data set, we don't just look at one single value of K. We look at a quite wide range of them. So in here, they looked at K from 2 all the way up to K of 7, because it allows us to visualize different elements of admixture modeled ancestries in the data set. So at K of 2, we see, of course, only 2 different types of modeled ancestry, which is generally in this data set looking at African versus non-African. At K of 3, for example, we now have this extra cluster that's added, which is primarily found in the San individuals, which makes sense since the ancestors of the San diverged from other modern humans a fairly long time ago compared to all the other currently living modern humans. And as we go up, we see more and more clusters that this algorithm will assign to different populations. And so eventually the Central African rainforest hunter-gatherers get their own cluster. We see different clusters of European as well as Middle Eastern populations. And so it can be a way for us to visualize the genetic diversity within our data set. And so I wanted to run admixture on 7 bridges, and luckily for me, there's already a publicly available admixture app for me to be able to use. However, I did need to make a couple minor revisions so that I could use the admixture app how I would like to based on how I would normally run it locally. And so I talked in the prior slide about applying the algorithm to evaluate different numbers of Ks, but how do we actually select a model that best fits our data? So the number of Ks that best fits our data. And if I take this figure from the admixture manual, what they would suggest is using something called cross-validation error. And what you're looking for is the replicate of K with the lowest cross-validate, with the first minimum value of cross-validation in your data set. So you kind of see this spike here, where at K of 3 is the minimum cross-validation, and then it starts to rise. So that would then suggest that K of 3 is the best fit for that data set. But another way that I'll run it in order to look at this is I won't just use one single replicate for each value of K. I'll use actually 10 replicates for each value of K on my data set. And therefore, I need to implement a random seed. And that was the first step that I needed to look at in order to implement the admixture app. So they already implemented the random seed option in the admixture app. But one thing that I first wanted to do, just so I never forgot to set it, was I changed it so that it was always a required setting, because you can run admixture without a random seed. And then the other thing that took almost an embarrassingly long time for me to figure out was how to actually get the string to be, the random seed to be truly random every time I would launch a job. And so normally I would use something on the local cluster like bash echo $random or $random, and that would give me my random seed. But that didn't work when I tried that on the cluster. So on 7 bridges, what ended up working for me was if I just typed time, and not $time, just time, as the string that went into random seed, and then it would actually give me a truly random seed based off of the time that each individual replicate was run. So that was the first step. And in order to evaluate this, I downsampled my data set to only a very small number of individuals and only a single chromosomes, just so that I could get things to run very quickly. But that was the first step. And then I kind of ran into some issues when it comes to the cost of running admixture. But before I do that, sorry, I just want to mention, in order to run admixture on the full data set, I needed to do some filtering. So first, as part of TopMed, they've jointly called Freeze 10 with the publicly available 1000 Genomes Project high coverage data, as well as the Human Genome Diversity Panel high coverage data. So this is important because it allows us to compare our samples to other populations from other regions in the globe. So coming from Eurasia and Oceania, as well as the Americas. We then needed to heavily filter because this data set had over 10,000 individuals and millions upon millions of genetic variants, which would just make the admixture algorithm take an incredibly long amount of time. So therefore, I restricted my analysis to only chromosome 1 to 22, as well as only biallelic SNPs And I also required that the minor allele frequency was greater than or equal to 5%. And then I also LD pruned the data. And so this shrunk the data set down to only about 419,000 variants, which is in a much better scale for admixture to be able to actually finish in a reasonable time. But what I then did is I wanted to assess how expensive it would be to actually run admixture so that I could do my cloud credits request, since I knew it would cost more than what the pilot funding was. So what I did is I ran 2 replicates of Ks 1, 2, 3, 4, 5, and 12, and then I assessed how long those 2 replicates took, and used the power law equation to then approximate how long this would take for each replicate out to even higher K values than I assessed with this test, so that I could then get an idea of how much this would actually cost. And so once I got my cloud credits, I then went on to 7 Bridges and started running this, running admixture from Ks 2 all the way up to trying to get to K of 20. But one thing I noticed very early on is that things were taking much more, were costing much more than I thought. And part of that was because spot instances being left on, which is in generally a good idea. However, at my single replicates of K of even just 2, which is the most simple replicate that I was going to run, things were taking over 10 hours, which meant oftentimes they were being stopped within the spot instance and then started to run, and then having to rerun over and over again, which actually started costing quite a large amount of money. And even if the spot instance didn't kill my job and have to restart, like at K of 4, things were costing much more than I guessed. So at K of 4, things were even taking over a day to run and cost $19. And if you think I need to now do this 10 times, and that's just at K of 4, and it gets progressively more complicated as you increase the value of K, trying to run this at K of 20 was not going to be very feasible. So this made me pause and think, what can I do to reduce the cost and make these jobs run quicker so that I can actually effectively use the spot instances. And in addition to that, just it being more expensive at lower values of K, I also, even trying to run this at the very high values of K, I ran into a number of issues where, for example, at K of 20, the job seemingly died without a legible error message after an entire week. So that's $100 that was ended up not being used because, or was used, but not for usable data. And then even at K of 16, the job seemingly stalled out. And after 13 days and $200, I decided to abort the task because it should not have been taking that long. And so, like I said, I had to pause and think, what can I do to make this run quicker and cost less money? And so one of the things that I kind of forgot is that admixture has multi-threading. And the reason I forgot is I'm used to running admixture on a data set with only a couple hundred individuals, and it might be array data, so even less SNPs than that. So normally you can run admixture on these much smaller data sets very quickly, and you don't really need to be too concerned about the multi-threaded mode. So now I wanted to implement the multi-threaded mode, which there was not currently an option in the publicly available app. So that's what I needed to develop to hopefully get this to run much quicker and therefore save me money so that I can run this at much higher values of K. One thing I want to note that a lab member of mine found is that if you feel inspired to start running admixture on your own data and need to use the multi-threaded mode, in one of their recent change logs to the program, they made a note that the number of threads that you can use, it scales smoothly up to 8 to 12. So I would suggest not going above 8 to 12 threads if you decide to run this program. So then I implemented multi-threading, which was relatively simple by just, if I go back here, by just adding an additional input to take this -j command. And so I first started running it on a very pared down small data set just to confirm it was in fact running with multiple threads when I asked it to, and it was. But then I went back to my K of 2 and said, all right, I'm now going to run 10 replicates with different numbers of threads. And so we can see with one thread, it took almost 17 hours to run and cost $10. But once I started adding multi-threading, I got the cost down to a little bit under $2. So it was quite a substantial reduction in time. And when you can run it within 5 hours, it often wasn't even, I could run it with spot instances on, and most of the times it wouldn't actually be stopped by the spot instances. As you can see, this one for here with 8 threads, it took 13 hours. That one was killed by a spot instance and restarted. So it was a little more expensive, However, nowhere near as expensive as when I was running this with only one single thread. When I go up to K of 6, see a similar thing. With one single thread, it was $26, but now I can get it down if the spot instance doesn't restart the job to about $5. And so it's a clear cost savings by running with the multi-threaded mode. And similarly at K of 8, it's a little bit more messy compared to some of the earlier ones. And that's because even with multi-threading, it still takes about 15 hours for the job to complete, which means if the spot instance does need to restart my job, the computation time can increase quite dramatically. Up to 43 hours was the longest one took. And that cost about $22, which is still a pretty big cost reduction from when I was trying to run this with only one single thread. And so in summary, what multi-threading allowed me to do is it allowed me to reduce the cost pretty substantially. So it allows me to be able to do more replicates with the cloud credits that I requested. And it also allows me to look at even higher K values. So I haven't yet run this past K of 10, but it does seem to be, it does reduce the overall cost. And one of the things that I'm now running into, and I'm not entirely certain how to calculate this just yet, but it's at what value of K will using spot instances no longer be beneficial, because even with multi-threading, the jobs are still going to take a fairly long amount of time. And so kind of managing that cost benefit. So at K of 8, if the spot instance doesn't need to restart the job, I can get it at $5.60. But if it does need to restart the job, then it's going to take about $22. So it's trying to figure out, that's kind of the step I'm at now, is trying to figure out what value of K will using spot instances no longer be beneficial. And then the goal is to eventually be able to run this program up to a K of 20, which is a very computationally intensive job. But hopefully now with multi-threading, it won't require the job to error out due to just the length of time that it's running. So that's what I have so far for running admixture on BDC, and how I've gotten it to be able to run much more efficiently by looking through what are the options to be able to make the program run quicker by implementing multi-threading. And I'm happy to hear any questions that you might have about admixture.
Awesome. Thanks, Daniel. Dave looks like he unmuted. Nathan is unmuted. If you have questions, of course, feel free to unmute yourselves, and I'll leave the floor for questions for Daniel, Dave, or any other part of the ecosystem anybody's wondering about.
I enjoyed that. Oh, go ahead.
No, go ahead, Nathan. I just was going to say you should go first.
I apologize for walking and zooming. You should never walk and zoom with your phone. Came off mute. I apologize. I'm doing more local admixture stuff, but this is good. This is good that it's all there. But my question is, you talked about the 900 million in the top med. So I haven't used that data set. I'm not familiar. I'm trying to, gear up to do some things, but at what frequency are you filtering to say 900 million, or is that all?
Oh, that is all of them. So okay. That is including singletons. So yeah, the bulk of that data is going to be singletons found in only one of the 180,000 individuals.
Okay.
Yeah.
And then I kind of missed it, obviously, because I was walking. So you use, or when you run admixture, you have a reference, right? Is it are you using 1,000 genomes, or what are you using?
I'm running it in the unsupervised mode, so I don't have a reference.
That's right. Yeah. You're doing K equals 2 or 3 or 4, whatever you're doing.
And so the goal is to get up to at least K of 20, which is probably about the max that we can do with this data.
Gotcha. Thank you.
But we did include individuals from the 1,000 genomes NHGDP which we won't use in a supervised way, but kind of after we run the analysis as a way to kind of interpret some of the Ks that will, or like clusters that will be found.
Sort of like a spiked in control, if you will.
Yeah.
Great presentation, Daniel. Thanks again for this, for doing it, and talking about the sort of challenges that you overcame on biodata catalyst. This is really great. And the spot instance, and by the way, if you're using Google, they're called preemptible instances. Those are kind of tricky, right? So the way the Seven Bridges platform treats it actually is it won't let you get preempted twice. So what happens is, you know, after 8 hours or whatever, you got preempted and you sort of lost all that. And it restarts as an on demand, which is a higher cost.
Okay.
So I guess this really wasn't a question, and more of a comment. Oh, I can send you, you may have already seen this. There is Amazon puts out a website which actually gives you the probability that you will be preempted for any given instance type. And it doesn't get that granular. I think it goes like less than 5%. So I always try to pick the ones that says less than 5%. So maybe just something to double check.
Yeah, that would be interesting to look at. I was talking with another lab member yesterday to just kind of further troubleshoot some of this as we're getting up to higher K values. And that was something that we were talking about, is it would be good if we could have some form of prediction on, like, does it give you, is it updated, not necessarily live, but relative to the time that you're using it?
Good, great. That was going to be my next point. You could also try potentially running it like at sort of off hours at like Sunday morning at like 3 in the morning or something, just to see. I think the traffic does affect it, and it gets updated in real time.
Okay, yeah. Yeah, because at the lower K values, when this can finish within only 5 hours, it's not going to really be stopped very much. But at K of 10 or K of 8 here, it was, even if it takes about 15, 17 hours, and there's subtle variation within each replicate based off how well that replicate fits your data. But yeah, at the larger K values, it definitely becomes much more costly when it has to be restarted.
I'll just make another comment if there's no other questions. You know, I think we've had feedback from other users. This is going back to the spot instance question. It's, you know, some users want to have the ability just to never run on demand. So I guess question for you, do you like the current behavior, or do you think it should be changed? So for instance, would you like it to keep trying spot instances, but with risking getting preempted? Or would you like it to say, all right, we got preempted, now just do on demand so I can get my results?
Yeah, I would think that option would be interesting for the lower values of K, when I'm much more certain that it would probably not get stopped more than once. But it is the higher values of K. I mean, if it's 15 hours at K of 8, it's going to take probably over a day once we get up to K, definitely over a day at K of 20. So only being able to be stopped once is probably I wouldn't want it to be getting repeated. It would probably be repeatedly stopped more than once, I would think.
Yeah, exactly. Yeah, that would be terrible, right? If you got got into a loop or kept preempted. I think maybe another solution would be to say, I don't want to ever run on demand. So if I get preempted, just let it stop.
Oh, okay. Yeah. Yeah.
All right, any other questions? Again, for Daniel, for Dave, or for any other part of the ecosystem, feel free to ask away. It can be on other topics as well.
Yeah, one question I had was, would you have done anything differently, like in the sense of, like, when you're doing this analysis, like, it looks like there are some optimizations that you found in this. So, for anyone who is going to start this new, like, how do you suggest, like, what's the path of, like, you're just right now, like, you're talking about one program, So again, like, does it have to be invented for each program when we try to investigate, like, what's the best path or how to do it, or based on your experience, like, say you want to do a GWAS analysis. So how would you extrapolate your learning and say, like, okay, here I learned this, or now, I'm in a better place.
Yeah, I think one thing I would always probably try to do is start small. So being able to run things on small sets of data to get quick feedback on how things are running. So one of the things that helped with testing out some of this aspect, not that I can really see cost savings with very small data sets, but if I just am trying to make sure multi-threading is working, if I run one replicate of K of 2 on the full data set, I have to wait 5 hours to kind of make sure the program is working as I intended it to. So that's a long wait time. So if I can pare down the data set just to make sure that the changes that I've implemented in the program are working, that's definitely one thing that I would do. And I guess thinking with big data, I think I would just start with looking at parallelization kind of ways or multi-threading kind of ways rather than starting to implement them without. I would probably start at the multi-threaded step next time.
One question for maybe David, like, there's a cost that when you run it on this, Google or Amazon platform, there's a cost. So does the 7 bridges, does it has a cost overhead, or like this platform does it, or is
So no overhead. So there should be no discrepancy whatsoever from the current rate on either Google or Amazon with what shows up in your billing group or on your task log.
Thank you.
All right, we still have about 12 minutes left. So again, the floor is open for any questions you have. I am going to launch a poll again, just about the interviews. It doesn't look like Emily, I think Emily might have left the call. She might have had another meeting, but if you are interested in participating in an interview about BDC, feel free to put your name and email into the poll, or you can contact Emily. Her name is in the chat, and I think she may be on the next slide maybe as well.
So can I ask you one question, Dave?
Yes, I just unmuted. Go ahead.
Yeah, so it's possible. I thought I haven't done anything on the biocatalytic on a platform yet. I want to try. I'm thinking maybe possible, for example, because given the the cost, I mean it's cost certain one thing. They also get familiar with the system, all the program. It's possible you create a toy data set, for example, maybe very small, but very representative, it's very small. So people can test all kind of calculation, including the Daniel's, the testing. So not run your own data, everybody, but because run your own data are later issues, but first get in the system and test the platform, the get familiar system with the data you have, and to give it to everybody can use. I think that'd be a great start.
That's an excellent point. And I can tell that you've sort of developed maybe apps on other places or have worked on some analysis before, because you always want to identify, it's called, like you mentioned, a toy data set or something that'll allow you to get through the process quickly and cheaply, and then sort of see potentially debug scripts. But you also want they're hard to find because you want it to be large enough that it will actually complete, right? And maybe it won't give you great answers, but it will actually complete. The best thing I can think of, I think we need more examples of this. There's a public project created by University of Washington, which is the Genesis tutorial, which really walks you through how to do the GWAS using those tools in either sort of workflow method or in the RStudio. in that project, there is 1,000 genomes, but they're VCFs for 1,000 genomes, but they're subsetted. So it's all, you know, however many subjects, like 2,900, but it's only sort of randomly selected genotypes for each chromosome. So that'll allow you to get through a GWAS without a tool failing, but just won't give you any great results, of course.
Yeah, maybe for example, this, you know, if I think it'll be great if you can have a toy data sets available on a platform. I think everybody, like including me, not worry about how, you know, because moving the our data to the platform may take some time, you know, because this but you know, get familiar with the platform first before move everything. I think this maybe take some time, you know, to understanding the system, which software available, and how to receive money. I think that's a bit great, very helpful. Yeah, very helpful.
Fantastic points. I may reach out to you about some ideas, and I made some notes. I think, you know, identifying those test data sets is key. Distributing them to researchers is also key. Like we have a lot of ways to get, you know, controlled data and even open data, but the open data is very large. So I think we need toy data sets that are used in sort of worked out examples, so people can see examples of how to use the platforms.
Yeah. So the other things is are on your platform. Do you have a UK biobank data?
This is a frequently asked question, and my understanding is that it's not for sure it's not hosted on Biodata Catalyst. And I always you have to sort of work out with them how you get access to it, and then there may be some interoperability mechanism we could work out. But there's no, I think it just there's so many like restrictions to it that you have to work out your own access to UK Biobank, and then sort of reach out and think about, well, how can we connect wherever, you know, it may be like a bring your own data type situation. I don't know.
I think so. All right. Thank you, David.
Okay, we have about 6 minutes left still, so if other people have questions, feel free to unmute or post in the chat. We do thank all of you for your time. Again, thank you so much to Daniel for the wonderful presentation. Thank you to Dave for joining us, for taking time out of your day to provide this great content. We will keep the room open. Oh, looks like Nathan unmuted again. Do you have another question, Nathan?
You have to watch me closely when I unmute you. So is it okay to ask science, or are we supposed to just ask cloud computing things?
I think anything is open right now.
Yeah, Daniel, do you care if I just ask about
Yeah, sure.
About your interpretation and stuff? So I was surprised when you went up to K7 that you saw so much Middle East in some of them. So I'm just thinking practically, when you're doing such a large data set and then you're trying to display it, right, to try to tell us what you've done so we can visualize it, are you picking, or how are you picking those that are displayed in your admixture plot? And then do those different ancestries that show up correlate geographically with sampling and stuff like that?
Yeah, it's really good point. So normally when I'm making an admixture plot, I guess I would probably, it depends on, I guess, how much space I might have in the paper that I'm writing. But one of the ways we could show things is kind of like this, where you show multiple K values, or what we'd also do is kind of select the best value of K through this cross-validation strategy that they suggest in the admixture manual, where you're looking for this minimum value of cross-validation. And so I might only present this value as well. Yeah. And then something like this might go in the supplement to show kind of what was getting broken up at earlier and lower values of K. And then oftentimes, depending on your sampling strategy, things may end up getting broken down based off of geographic regions as well. If you don't go up to high enough K values, then that will definitely be some level of clustering that you might see at a certain point. But a lot of that will also be impacted, and what level and ordering of things you see and what gets available at or identified at different levels of K will be very influenced by your sample, the samples in your data set. And if certain populations that you've sampled are at much higher sizes than others, then that might influence what gets identified at lower values of K versus higher values of K.
And then if you ever moved on to things like local ancestry, would you then use your optimized in the cross-validation sort of as your reference, probably?
I have done that in the past, yes. If you want to,
I mean, because does that cross-validation thing imply that like the Middle East, because then the values went back up much higher, so there's just not as much strength in those ancestry?
Yeah, I should probably say this cross-validation comes from the admixture manual.
Yeah.
So that this cross-validation is not related to this plot. I don't actually know the cross-validation for this admixture analysis.
Fair enough.
But I in prior projects, I have done a strategy like that when I wanted to do local ancestry, was first run admixture to try and identify groups that are less admixed than others and use those as references in something like local ancestry.
And then I guess when you're interpreting as you go up in K, you know, you first see the green start to go away. So it's pulling from the green to go to the yellow. And then later on, you start to see the red going away. So is that sort of fair to think about? Those are the ones that are harder to assign ancestry to, or more similar to each other ancestry wise?
Yes, and some of that in the orders of things will depend on sample sizes in terms of what's getting kind of pulled away. So I guess like so things that were once green and are becoming different colors are different African populations, since green is generally in the African ones. So the San get their own, and then the central rainforest hunter-gatherers do. The East Africans do as well with the blue clusters there. I think I don't remember the sample size in this data set, but since there's so much more genetic diversity in sub-Saharan Africa, but also if you've sampled much more, then those are kind of the populations that are going to get identified a little bit earlier in the admixture plot compared to later. So yeah, definitely, I'm not sure if we can say too much about difficulty to interpret, because it is so much, it can be very largely impacted by your sampling strategy, and the composition of your data set will determine what you can identify at different values of K.
Thanks for that.
So I have more questions, Daniel. So when you do this determine the K, are you assign equal number of individuals in each country? For example, minimum we have at least 100 individuals from one country, right? So you pull all data from one country. Do you have the limitations or just put them together?
I don't have any limitations. We run it on everybody in the data set. These groupings, so the admixture algorithm doesn't know any of these groupings that we've added on this figure. This is groupings we've added later to help with visualization of the results. So for this plot, there hasn't been any downsampling of any specific groups. That is a strategy you could try to use if your data set has very different sized populations, but in general, I normally just kind of run it with everybody all at once, and then kind of evaluate the results as it goes.
Yeah, one thing, for example, if you don't, for example, by accident, you have maybe a group individual, let's say for example, from America, for example, the Native American, for example, or is from Asian, they are because they are able to focus based on the reference. Are you able to identify this not from particular African continent, or from another part of the continent?
Well, so I think what we can do with what we're viewing with admixture is we can get a general sense of how similar certain individuals might be more towards others, or I'm trying to figure out how to, not quite sure actually how to answer that. We can definitely, we can use this as a way to kind of get a summary of the data set and get a sense of what are the different types of components you might see, but we would also combine this with something like principal components, which would tell you similar but slightly different signals as well. But yes, in the past, I have used this on data sets of different populations from throughout South America as well to look at these kind of general genetic structure within the data set.
All right, thank you. Nice work, very nice work.
Thank you.